All right. Hello, everyone. This is your professor, Dr. Gallenstein, and today we are going to do lecture number 4, Multivariate Regression Model. Now, just to give us a little bit of a primer, I hope you remember from last lecture when we introduced the concept of econometrics and the concept of running a regression analysis. We looked at a simple regression model in the last lecture. This was a model in which we had one dependent variable and we had one independent variable. And we were using the model to see if there was a significant statistical relationship between the dependent variable and the independent variable. Specifically, I believe we looked at wages and education. Are wages and education related? Now, and what we talked about was how in econometrics, what we're trying to do is develop some model or some function of a dependent variable, of some variable of interest, like wages from last lecture. And we want to develop a model of wages, something that will describe wages, something that tells you the other factors that influence or affect wages. And in our simple model, we only had one regressor. We only had one variable, and it was, in our case, education. And we concluded last lecture with the question, well, do we think that this is a good model? Does it do a good job of explaining wages? Does a model that just has education do a good job of explaining wages? Do we really think that wages are only a function of income? Only a function of education. Well, we can pretty quickly think about that and realize, no, I think that that's not a great model. I think that lots of other factors are going to affect wages. So I do not think that a model that has only education is a very good model. I think that wages are going to be determined, or they're going to be affected by a lot of different variables. So let's begin this lecture by thinking, okay, can we do better? Can we make a better model? Can we make a better model of wages? Can we make a better model of some other dependent variable that we might be interested in? Can we make a better model than just a simple regression model? So if we want to set out to do that, all right, let's just remind ourselves here. We had a simple regression model last time, looking at income or wages as a function purely of education. But this is probably too simplistic to be very helpful. There are probably lots of factors that will affect education. Well, what other factors might we include? Let's think about it first. What other factors might we include? How much money someone makes, someone's wage might be affected by how many years of experience they have. It might be affected by what area of the country they live in or what sector they work in. It might be affected by their innate ability, their intelligence, their charisma. It might be affected by their social network. It might be affected by a lot of different factors. So a model that has only one independent variable is probably not going to do a very good job of explaining or predicting income. It's probably not going to be a very good model. Well, let's think of some other things. Okay, now let's state a multivariate regression model. Okay? And we're going to say that, all right, income is a function not only of education, but it's also going to be a function of experience, and it's going to be a function of gender. All right? So now we're going to use a multivariate regression model that has multiple independent variables. So we have the same dependent variable, income, but now it's a function, yes, of education, but also experience, and a dummy variable here that there's one if the individual is female. So now it's a function also of gender. All right, so then here is a multivariate regression model. It is a linear model. We're adding terms. Okay. It's a linear model, linear in the parameters. Okay. and it is a function of multiple different independent variables. All right, now just by intuition, we can expect that this model would be a better model of income. Because just by intuition, we can say, well, certainly there are other things that affect income other than education, and now we are including some of those other variables. We are including other important, potentially important, or relevant, potentially relevant factors in our analysis when we do a multivariate regression model. And so a multivariate regression model that includes important and relevant factors will probably do a better job of explaining income. It will probably give us a better model for potentially predicting incomes, for example, because it represents a more thorough or more complete function for income. Okay, so that lays our foundation. That lays the foundation. We want to build a better model, and so to build a better model, we're going to include some more variables. And we're going to include more variables that we think are relevant, important, things that affect or are influenced by or are closely related to the dependent variable, in this case, income or wages. But now, let's be a little bit more clear. Let's think more about this. Let's talk about model specification. When I say model specification, what I mean is actually specifying or actually writing down, determining what your regression model will be. And so when I say that, I mean, at least for now, what I mean is what variables am I going to include? Now that I'm doing a multivariate regression model, I could include lots of different variables. So then this becomes a real question of, well, what variables should I include? What are the different factors that I think will affect or relate to income? I need to think carefully about this. I need to think carefully about model specification. All right, so then we have to think, well, how do we pick our independent variables? What are the independent variables that we will include in our model? Well, as economists, we always start the design of our economic models based on economic theory and sound, reasonable, theory-based, if you will, intuition. So we always begin writing our models by thinking first. We always think first. We always sit back and think carefully about the question that we are researching. We might even read some papers, we might read news articles, we might read some information that is relevant to the topic to give us some intuition and to give us some theory behind our model. So if we're thinking about income or if we're thinking about wages, we need to sit back, and before we write out our model, we need to sit back and think. Based on economic theory, what are the factors that would affect, influence, or drive wages? Based on sound intuition, what do I think will affect wages or income? I always sit back first and think. Okay? And then I will write a model, or I will write a couple of models based on that intuition, based on that theory first. Now, once I've theorized, once I've done my thinking, I've done my theorizing, maybe I've read some literature on it to give me some grounding in some ideas, then I might, quote, let the data speak. I might start to look in my data and see, okay, do I have any reason from my data to think that my model makes sense? All right, I'm going to show you when we do our Stata presentation later what I mean by letting the data speak. All right, but just to drive this point home, we always think and use our intuition and use of past research and economic theory to write our models first. Okay, so then let's make this presentation more practical. And we're going to do that by using the same data set that we looked at last time. And this time I'm just going to make really clear what we have in our data set so that we can begin to think about what would make for a good model. All right, so let's imagine we're looking at a model of wages. We want to explain wages. We might even want to predict wages. Okay, we want to figure out, well, what are the factors that influence wages? We might even want to say, well, what are the most important factors? We might even want to compare which one's more important than others. Okay, so then let's look at our data set and begin thinking. All right, in our data set, we've got, how many variables we got here? We've got 1, 2, 3, 4, 5, 6, 7 variables in our data set. One is wages. That's wages measured in dollars per hour for each individual. One thing you'll notice here is I've got a little subscript here, subscript I. What I'm using that subscript for is to indicate that there are different values for the variable wage for each individual I. So I give it a subscript I. It's an index. All right. I've got education measured in years. I've got experience measured in years. I have ethnicity captured by this variable non-white. It's a dummy variable. It equals 1 if the person is not white or not Caucasian. Okay. I've got female measurement for gender. It equals 1 if the person is female. And I have married. Married is a dummy variable. It equals 1 if the individual is married. All right. And then finally, I have job. Job is a categorical variable. It has variables 1 through 4, where 1 through 4 each indicate for some different job, some different job category. All right. Now, with this information in hand, let's begin thinking about what would make a good model. Before we even look at that next slide, let's think about this. What would make a good model? What would be a good model of wages? What do we think affects wages? What do we think affects wages out of this list of variables? What do we think affects wages even for variables that aren't included here? Let's think. Well, I would say for sure education. Education is a great place to start. I'm sure that education is going to impact wages. I think experience is going to have impact on wages. Those are really clear for me. The rest aren't perfectly clear. If I control for wages, if I control for education and experience, those other variables might not be significant. They might not actually affect you. Okay, so then let's think about that. Now, we might be able to think of some other variables, maybe innate ability. Maybe the job sector that you work in, that might affect it. Okay, but let's start. Let's do our first multivariate regression model just as the most simple. All right, let's just start simple, and let's take the variables that we are the most confident in. We are most confident that education and experience will affect wages. So we might write our model right here. This is our first multivariate regression model. All right, we've got education and experience. All right, now that means that every other factor in our data set and factors that aren't in our data set are in that error term. All of the factors, so gender, ethnicity, job type, marital status, and then other factors that we don't have data on, things like innate ability, intelligence, maybe creativity, charisma, social network, what country they live in, what city they live in. All kinds of things are going to affect wages, but we don't even have data on them. All those factors, even the ones that we don't have data on, they're all going to go into that error term. All right, that error term accounts for them. But what we've said here is, okay, this is our first shot at a multivariate regression model, and we're including the 2 most important variables. We're going to let everything else go into the error term. All right. Now, but for reasons that we will explore later, so next lecture we're going to talk in a little bit more detail about how important this is, we really do not want to exclude important variables. It's very important to us that we do not exclude important variables. I'll make that more clear next lecture, but to suffice it to say for today that it is very important that we do not exclude important, relevant variables that really do closely relate with wages. All right. So then now we've written this model and it has two variables that we think are very important. But let's think a little bit more. Maybe there are some other variables that we can include. Maybe there are some other variables. Maybe they're not quite as important as education and experience, but they are important and they're relevant. And because I just said we don't want to include we don't want to exclude important variables. Let's think of another model. Let's think of maybe even a better model that doesn't exclude important variables. All right, so let's think again. What else might matter? What do I not want in the error term? Well, okay, let's go ahead and include our non-white variable and our female variable. All right, we're going to include those two. We think those might have an effect. Now, they might not be as important as education and experience. They might not be as important as education and experience, but we're going to include them because I think that they might have an effect, and we don't want to leave out anything that's important. All right. Now, with that, all the other factors are in the error term: job type, marital status, innate ability. All those other kinds of factors are going to end up in the error term. All right. Now, with that said, we've had a nice discussion of the variables from our data set that we might include. But I want to go a little bit more deeper into it. So far, we've only talked about explicit variables. We've only talked about explicit variables in our data set and then variables that aren't in our data set. Okay. But what we can find is that actually a good model might include interactions between different variables. So let's think about that. What does that mean? Let's talk about interaction terms. All right. Now this is another kind of variable that we might include in our model if we think that it's important. All right. Now we would include an interaction term if we think that two or more, but typically two different independent variables interact with each other. If we think two different interaction terms interact with two different independent variables interact with each other, we will include an interaction term. An interaction term captures the interaction between two independent variables. So let's make this more clear. Let's give an example to drive this point home. Now let's think. I got two examples here. Perhaps education becomes more valuable to you as you get more experience. Or perhaps the alternative is even more intuitive. Perhaps education becomes less valuable to you as you get more experience. Let's think about that. Let's use our intuition. Does this make sense? And I'm going to use the second example. Perhaps education becomes less valuable to you as you get more experience. All right. Does that make sense? Let's think about it. When you graduate from college, you don't have any experience usually, unless you got an internship, which I recommend. But let's say you've never had an internship, and when you graduate college, you have a nice long set of your life being educated, around 16 years of education. So you have a lot of education, but no experience. Now, each of those years of education are going to be pretty valuable and pretty important to you. When you look for jobs, those jobs are going to put a lot of weight on your education because you don't have any experience. Okay, so each of those years of education are going to be very important to you. They're going to have a huge effect on your wages. Each of those years of college, or the fact that you have a college degree, is going to affect your wages a lot because you don't have any experience. Your education is the only thing that your future employer is evaluating you on because you do not have any actual experience in the field. And so every year of experience or every degree that you've accumulated, when you have no experience, every amount of education is going to be worth a lot to you. But now let's imagine the opposite extreme. Let's say you've been working for 10 years or 20 years in your field. At that point, you have accumulated a lot of experience. At that point, when you apply for a new job or you ask for a raise from your employer is a lot less concerned with how much education you have and is a lot more concerned by the amount of experience that you have. And so each of those years of schooling are going to be worth less to you because now you have a whole bunch of experience. From that example, do you see how experience and education might interact with each other? It might not be that that wages is just determined by education and experience, where those two are totally separate from each other, but it might be affected by education, experience, and the interaction between education and experience. Let's think of another example, hopefully to drive this point home. Perhaps experience matters more if you work in a certain sector of the economy. Perhaps in manufacturing, experience matters a lot, but experience doesn't matter a lot in, let's say, the service sector. In manufacturing, experience matters a lot because they are looking for people that know how to use the machinery and are able to manufacture the items that the company manufactures. They want people with active, hands-on experience, and that experience is very valuable. The more experience you have in manufacturing, the much more productive you are. But in the service sector, you don't make a lot more money if you have more years of experience. If you go into a restaurant, the waiters that have been there for 10 years probably don't make that much more than the waiters that just started yesterday. So experience matters a lot in manufacturing and not a lot in the service sector, maybe. All right, perhaps that's the case. But this illustrates that there might be interaction effects between different independent variables. And we might want to account for that in our model specification. When we determine what variables to include, we might think, well, gosh, these two independent variables, they interact with each other. So let me include an interaction term. Now, an interaction term is pretty straightforward. All you do is multiply the two variables that you think are interacting with each other. You're just going to take those two variables and multiply them together and create a new variable that captures the interaction between the two. All right, so then let's see what this looks like. I'm going to use the first example. Perhaps education becomes more or less valuable as you get more experience. Well, let's throw that into our regression. We've got wages as a function of education, experience, and then education interacted with experience. So now we've accounted for it. There's our interaction term. All right, now our intuition makes it clear to us that we think this might be a really important variable, so we're going to include it in this model. All right, now there might be some other things that we might do with our data. All right, moving on from interaction terms, and now let's talk about another one, additional functional forms. All right, let's say that we believe that one of our variables has a non-linear relationship with the dependent variable. A non-linear relationship. That means that as this independent variable goes up, wages doesn't necessarily always go up. Sometimes it goes up, sometimes it goes down. It's non-linear. Usually we assume that the relationship is linear. More education means more wages, period. No matter how much education you have, more education always means more wages. We assume it's linear. It's a straight line. But sometimes it's not a straight line. Let's take an example. All right, thinking again about wages. As wages, okay, so imagine the wages increase as experience goes up. Now that makes a ton of sense. It's very intuitive. As your experience level goes up, your wages are going to go up. Okay, but now, is that always true? Perhaps there's a point. Perhaps there's a point at which additional years of experience actually doesn't help you, actually doesn't increase your wages, but maybe even hurts your wages. So imagine that you work in the manufacturing sector, and when you start, getting any additional years of experience is highly valuable. But you might get to a point where maybe you say you have 40 years of experience, 50 years of experience. With all those years of experience, it might be hard for you to adjust or to accommodate new technologies, changes in the way that manufacturing is taking place. When someone who is maybe fresh out of school, freshly educated in some of the more modern technologies, is able to adjust and learn better than someone with a lot of years of experience who's maybe kind of set in their ways from earlier in their career. At that point, additional years of experience might not be that valuable. The same thing might be the case with education. Or it might be the case with age. So you might expect that as people get older, they make more money, but only up to a certain point. Maybe you make more money as you get older up till around the time that you retire. And at the time that you retire, instead of making money, you are spending the money that you've saved. And so your income goes down at some point. It's non-linear. It goes up for a while, and then it goes down for a while. So so if we think that such a non-linear relationship exists, we can include what we call a squared term to capture the curvature, to capture the non-linearity. That was not the only thing that we could do to run this. But this is going to be one of the most common ways of capturing nonlinearities. So if we use our example of experience, here we've got experience and we just square it. Experience times experience. We have experience squared. And we would include experience squared in our regression. All right? And this will capture the nonlinear relationship between experience and wages. Let me make this more clear. Here's a graph. There's a scatter plot of some dependent variable and some independent variable. So let's say that y is wages and x is experience, given our example. So now what we might find here is that, okay, yeah, as experience goes up at first, wages go up. But you reach some point, you reach some point in experience where all of a sudden additional years of experience doesn't really help you. And at some point, it starts to hurt you. At some point, additional years of experience actually hurts your wages rather than helps your wages. Or we could think about this as age, as I said before. As you go into your 20s, into your 30s, you make more money. Into your 40s, you make more money. But you reach some pinnacle point in your career where you start making less money. All right, so if we think that there's this nonlinearity in our data, if we think that there's some nonlinear relationship between wages and some variable, we might include a squared term. All right, now what we've done so far is we've kind of laid out some a bunch of different variables and some thoughts about what variables we should include. But now, using that point I mentioned earlier where I said, look, it's really important that we don't exclude relevant or important variables. It's very important. We might take that intuition, that important point that I made, we might take that and think, well, why don't we just include everything? Why don't we include every single variable in the data set? Why don't we include every single variable in the data set and interaction terms between all the variables and squared terms between all the variables? We just include everything that we can think of. Here I've got a model like that where here this includes variables. This includes all the variables in our data set. Now we could also start interacting them in interaction terms between all the different variables. All right. Sometimes we call this the kitchen sink model. It's kind of an American idiom. The kitchen sink is typically referred to. The kitchen sink is kind of filled with all the dishes, and so, anyways, we call this the kitchen sink model because it has everything in it. All right, and the kitchen sink has everything in it. So this is the kitchen sink model. All right, it just has everything in it. Why don't we just do the kitchen sink model? Why don't we just throw everything in there? Well, before I answer this question, let me make a couple quick points on the notation that I have here. Let me take an aside for the moment and clarify something. So I'm gonna leave you with a cliffhanger for a couple minutes, and then I'll answer your question why we don't use the kitchen sink. All right, first I just want to clarify. All right, we are including all variables in our data set. We are only missing variables that we do not have in the data. So inability. That's that arrow should be pointing at the epsilon there. All right. Now let me just clarify something. Let's clarify what I mean with this term here. This term might be unclear. What we've got here is we've got this variable job, and job is a categorical variable. It is composed of either numbers or words that indicate different jobs. And in our data set, we happen to have 4 possible jobs. Okay, we can't include a categorical variable in the regression. We can't include a categorical variable because the numbers don't mean anything. And differences between the numbers don't really mean anything. All right, so this is a nominal categorical variable, if you remember from the first lecture. So we can't just include it in the regression. What we need to do is transform it into a series of dummy variables. I will show you this in the demo at the end of the lecture. We need to transform it into a series of dummy variables where each dummy variable indicates one of the possible jobs. In our data set, we have 4 possible jobs. So we will create a dummy variable for each job, one dummy variable for each job excluding 1, and include those 3. Okay, so we have 4 possible jobs, so we will create 3 dummy variables and include those 3 dummy variables in the model. Now, instead of writing that out, I just use the sum notation. The sum from j equals 1 to 3. All right, I should have a little bit of a typo here. I'll just correct this real quick. All right, so the sum from j equals 1 to 3 will give you beta 6 plus the first job dummy variable, plus beta 7 times the second job dummy variable, plus beta 8 times the third job dummy variable. Okay, so this includes 3 of the 4 dummy variables. All right, now you might be asking yourself, well, why include only 3 dummy variables? What we want is to avoid what's called the dummy variable trap. Why don't we include a dummy variable for all 4 jobs? Well, this will be called the dummy variable trap. We're going to go more into detail to exactly why we can't fall into the dummy variable trap. But suffice it to say, for now, you cannot include a dummy variable for each element of a categorical variable. This will give you perfect multicollinearity. We will discuss this more in a later lecture. And I will demo the problem in today's demo from Stata. All right. So with that aside in place, why don't we include everything? Why don't we use the kitchen sink model? All right. Now the problem with the kitchen sink model is that we are including irrelevant variables that don't explain wages, variables that aren't important. Now what's wrong with including irrelevant variables? Well, it's not a tremendously bad problem. It doesn't make any of your estimates biased. We'll talk more about bias in the next lecture. But it will make the regression less efficient. Again, we'll make that more clear in the next lecture. But basically, if we include too many variables, it becomes more difficult to us to test our hypotheses. All right? It becomes difficult for us to test our hypotheses about the values of beta 2 and beta 3 and beta 4, etc., if we include a bunch of unnecessary or irrelevant variables. So the trick for us as economists, the trick for us as econometricians, people that use econometric models, the trick for us is to come up with a model that includes relevant and important variables and excludes irrelevant and unimportant variables. We can't just include every variable that we can think of, because then we start to get an inefficient model. All right. Now, in the future lecture, we're going to go into the mathematical details, and I'm going to make those points more clear. But right now, we're doing the conceptual overview. So we want a model that includes all the relevant variables, and we want a model that does not include a bunch of irrelevant variables. Okay, now with that said, with that foundation laid, let's go through and talk about how do we interpret the coefficients from a multivariate regression model. All right, how do we interpret the coefficients from a multivariate regression model? Well, when we run our model, when we do our estimation, we're going to get estimates for all the betas in the model, right? And so we have a single coefficient for each independent variable. And we will interpret each of those coefficients in a very similar way as we would before, as we did with the simple linear regression model. So for example, let's say beta 1 is the change in y given a unit change in x. So using our example, beta 1 is the amount that wages increase given a 1-year increase in education. So to interpret this, to interpret beta 1, that's the estimate of beta 1 hat is the estimate of beta 1. We would say wages increase by beta 1 hat per hour for each additional year of schooling, holding all other variables constant. So here we just want to reiterate that now we need to interpret the coefficient. All right, so when we interpret the coefficient, we assume that it is the change in the dependent variable given a change in the corresponding independent variable, assuming that all of the other variables are not changing. We call this the ceteris paribus assumption. That means beta 1 hat is the change in the dependent variable given a 1-unit change in the independent variable, holding all the other variables constant. Okay, we can use some calculus. We can use some calculus to help us with interpreting these coefficients. Okay, now in a minute when we start to interpret the coefficients on interaction terms or the coefficients on square terms, it'll become a little bit more difficult. So now I'm going to bring in some calculus here. Specifically, I'm going to bring in derivatives. Now, if you're really rusty on your derivatives, I would recommend going to one of my other videos on my YouTube channel for a derivative review. Okay. Now, with that said, let's take a derivative. Now, consider the following model. This is the first multivariate regression model that we specified in this lecture. All right, wage is a function of education and experience. All right, we want to know how a change in education affects wages. Well, one way to do that is we take the derivative of this wage model with respect to education. Now, if you take the derivative of wage with respect to education, that would be this term here, the derivative of wage with respect to education, that equals beta 1. The derivative of this equation with respect to education is beta 1. All right, and now we know that the derivative is the change in the dependent variable given a unit change in the independent variable. All right, so the wage, the derivative gives us the slope. It gives us the change. It gives us how much wage changes when you change education. That is beta 1. That'll be really useful as we interpret interaction terms. How do we interpret the coefficients on interaction terms? This can be kind of complicated, a little bit difficult. So let's consider our model with the interaction term between education and experience. So you can see here we have wage as a function of education, experience, and the interaction between education and experience. Now the easiest way to interpret beta 3, that's the tough one, the easiest way to interpret beta 3 is to take the derivative of wage with respect to education or experience. You could do one or the other. So let's take the derivative. If we take the derivative of wage with respect to education, what we get now is beta 1 plus beta 3 times experience. If we take the derivative of wage with respect to experience, we get beta 2 plus beta 3 times education. All right. I hope from calculus, from derivatives, you can see that as we take the derivative here. Like I said, go and review some derivatives with my other video. You can find it on my YouTube channel that can help make this more clear. All right, so we can take the derivative with respect to education or with respect to experience to get an idea of what beta 3 means. All right, so let's go into some detail here. Let's consider, we want to know what is the impact of education on wages. So in this case, beta 1 is the increase in wage given a 1-year increase in education when someone has 0 years of experience. Let's think about that. If experience equals 0, then beta 3 times 0 is just 0, and you get just beta 1. So if someone has no years of experience, beta 1 is the amount that wages increase with an increase in education. All right. But now, what's beta 3? How do I understand beta 3? Beta 3 is how much more wages increase given a 1-year increase in education, given a 1-year increase in experience. Okay, this gets kind of tricky. Beta 3 is the additional amount that wages will increase or decrease if beta 3 is negative. Let's assume beta 3 is positive right here. If it's negative, the sign is just the opposite. All right, but let's assume, just for the sake of the explanation, that beta 3 is positive. All right, so beta 3 is how much more wages will increase with an increase in education given a 1-year increase in experience. So if I increase my experience by 1 year, beta 3 tells me how much more education will affect wages. Or if beta 3 is negative, that would be how much less education affects wages when I increase my experience. Let me make this clear using the example I used before. So before, just using the intuition, I was saying that when you first get out of college, your education is going to be very important in determining how much money you make. It's going to be very important because your future employers will not have experience to evaluate. You will not have experience that will allow your employer to evaluate you. Okay, so education is going to be very important. In that example, I'm saying that when experience is 0, all right, I'm looking only at beta 1. Beta 1 is going to be large. Beta 1 is going to be large. That means your education, when you have no experience, your education is going to be very important in determining your wages. All right, but then as you increase your experience, if you increase your experience by 1 year, or 2 years, or 3 years, or 10 years, as you increase your experience, how important your education is will decrease, using that example from earlier. This would be where beta 3 is negative. So that would be, let's say that beta 1 is 10. That means every year of education that you have, when you have no years of experience, every year of education that you have is worth $10 an hour. That's a little high. Maybe it's $2. Okay. Beta 1's 2. All right. But then as you start to get experience, how the effect of education on wages starts to go down. The more experience you have, the less that your education affects your income. So the beta 3 would be negative, and maybe it would be negative like 0.1. So every time you get a year of experience, the value of your education goes down a little bit. All right. So beta 3 measures this interaction. It measures how much more or less education affects your wages given a change in experience. All right. That's tricky. So if you have some questions, please come and ask me. We could do this the same way. Let's do the same thing, but just reversing it. All right. I can interpret beta 3 in two different ways because it's connected to an interaction term. So now let's take the derivative of wage with respect to experience. In this case, I want to know how much does experience impact your wages? Well, you know what? Actually, the same principle might hold here. Let's say, just using our intuition, let's say that experience is less valuable to you with the more education that you have. Let's say if you have a master's degree, your employer's not as much concerned for how much experience you have because you have a master's degree. Okay, so the how much experience affects your wages might be influenced by how much education you have. And experience might be less valuable to you if you have more education. So let's look at this. If that's the case, then when education is 0, let's say you have no education, you have 0 years of education, experience might be really, really important. It might be a very important factor in determining your wages. So beta 2 might be relatively large. But then, as you get more education, experience becomes less important. It's a less important factor in determining your wages. And so beta 3 would be negative. And as education goes up, the overall effect of experience on wage goes down. Because you have beta 2 minus beta 3 times whatever education is. All right. So beta 3 is how much more wages increase or how much less wages increase given a 1-year increase in experience, given a 1-year increase in education. Okay? Let me know if this is tricky and we can talk about it some more. All right, how about interpreting a squared term? How do we interpret a squared term? Again, the easiest way to interpret beta 3, all right, looking at the model that has this experience squared, the best way and easiest way to interpret beta 3 is to take the derivative of wage with respect to experience. Okay? Actually, I need to correct a typo here. This should be experience. Okay. All right, so when we take the derivative with respect to experience, so in this case, beta 2 is how valuable experience is to you when you don't have any experience. So this is basically how important is that first year of experience? Well, I bet 1 year of experience is going to be worth a lot. Your first year of experience is going to increase your wages quite a bit. Beta 3 is going to measure how much more or less wages increase given a 1-year increase in experience, given how much experience you have. So what you might find is that every additional year of experience is worth less to you than the first year of experience. So beta 3 kind of measures that. It kind of measures how much more or how much less each additional year of experience is as a function of how much experience you already have. So we might find that, okay, beta 3 is negative. When your experience goes up and you don't have any experience to begin with, your wages are going to go up. But when you have a lot of experience, ultimately the effective experience on wage might actually become negative because beta 3 is negative. And so if the number of years experience you already have is really high, then the total effective experience on wages could be negative. Okay. Now, that is it for specifying the model and interpreting the coefficients from those models. Now that we've done that, let's talk about hypothesis testing in the context of a multivariate regression model. All right. Multiple hypotheses. All right. Now, when we have a multivariate regression model, we can test multiple hypotheses. We can test for the significance of each individual beta, each individual coefficient. All right. We can look for the significance of each individual beta, each individual coefficient in the regression using the same method that we used for a simple regression model. The same method that we use for a simple regression model. We use the t-test, and we test whether or not each individual coefficient is significant. So that is pretty straightforward. We're basically doing the same thing we did with the simple regression model, but now we're just doing it for more coefficients. Okay, but when we have a multivariate regression model, we can do some interesting additional hypothesis testing. So let's use some experience. Let's use some examples. Okay, I'm going to look at two different examples. One is a single linear restriction, and the other is a multiple linear restriction. But let me make this clear what this is. Let me fix that. All right, now let's consider a model. We're going to get out of the wages example, and now we're going to look at GPA. We're going to look at student GPA. All right, looking at student GPA, let's say that a student's GPA is a function of whether or not they have in-class lectures. So this lecture variable is a dummy variable indicating whether or not, or the number of classes that they take in the classroom with a live lecture. All right. And then it's also a function of how many classes they take online courses. Okay. And how many courses, how many hours they spend studying. And then finally, it's a function of what their major is. All right, here's a reasonable model for GPA. GPA is a function of the number of classes that the student takes in lecture format, the number of classes the student takes in online format, and the number of hours that they spend studying, and the major that they've chosen. All right, here's a somewhat straightforward function or model of a student's GPA. Now, we can do our standard hypothesis testing on each of these coefficients. We want to know the relationship between GPA and lecturing. Beta 1. There we go. We just do our hypothesis testing on beta 1. And the same thing for beta 2, and beta 3, and beta 4. We can test each separate hypothesis. All right. All right, so if we want to know if lecture-based courses and online courses are positively correlated with GPA, we will run this regression model and perform hypothesis testing on lecture and on online separately. Standard, just the way we did before, just with multiple variables. But here's the thing. We might want to know more than that. We might not be interested in knowing, well, whether or not GPA goes up with lectures or with online courses, but we might want to compare them. We might be really interested in knowing whether or not lectures do a better job of improving students' GPA or online. We might want to know whether or not the relationship between lecture and GPA is the same as the relationship between lecture and online. We might want to know which one of them is bigger. For this, we can use a single linear restriction. Do a hypothesis on a single linear restriction. All right, this is what our null hypothesis would be. The null hypothesis is always that there's no difference, so there's no impact. Whatever it is that we're interested in, the null hypothesis is always that it's not there. So the null hypothesis in this case is that lecture-based courses and online courses have the same relationship with GPA. In that case, what this means is that beta 1 equals beta 2. All right, this is our null hypothesis. We're saying that one beta is equal to another beta. All right. The alternative hypothesis is that there is a difference. All right, beta 1 is not equal to beta 2. For this, we would use a t-test, and this would be our t-statistic. All right. Now, we might be interested in doing more. So let's use the same example. All right. But now we might think, okay, I'm interested. So I've got these two variables, and these two variables proxy for different kinds of instructional forms. Different kinds of instructional forms. So one is like in-class lecture and one is online. Two different kinds of instructional forms. Now, in the last example, I wanted to know, okay, are they different? Do these do these differ? Is there a difference between the relationship between GPA and beta 1 or the relationship between GPA and beta 2? But now I might ask the question, well, does the classroom instruction matter, or does the type of instruction, does the format of instruction matter at all? Does the format of instruction matter at all? Once we've controlled for the number of hours that the students spend studying and the major that they've selected, does it matter what type of instructional format it is? If we want to know if the type of instructional format matters, we would need to do a multiple linear restriction. This is what our hypothesis would be. We would say the null hypothesis is that the combined effect of lecture and online, the joint effect of lecture and online, is 0. What that would mean, that's our null hypothesis, what that would mean is that beta 1 equals beta 2. And those two equal 0. That means both beta 1 and beta 2 are both 0. That's the null hypothesis. The null hypothesis is that once I control for hours and major, then the instructional format does not matter. All right, so beta 1 equals beta 2 equals 0. That's the null hypothesis. The alternative hypothesis is just simply, we just say that it's false in this case. Now, to test this multiple linear restriction, we use what's called an F-test. An F-test functions in a very similar way as the t-test. Basically, we produce an F statistic, which I'll show in a future lecture. And then we perform a hypothesis test in a similar way to a t-test. We compare our F statistic to an F distribution. We calculate a p-value. And then we see whether or not our p-value is smaller than our significance level. And if it is, we reject the null hypothesis, or we fail to reject the null hypothesis. Okay. Now, with that said, I just want to add to our conversation a little bit here on statistical significance. I've alluded to it in the past couple lectures. It's a very important concept throughout the course, but I just want to take this moment to broaden our understanding of it before I move on to the demo, to the practical demo. I want to make a distinction, before we go too far in this class, I want to make a distinction between statistical significance and practical significance. Now, we know what statistical significance is. Statistical significance is where we've rejected the null hypothesis that the true value of the coefficient is 0, or that the true relationship between the different variables is 0. All right, statistical significance is where we conclude that we have evidence to suggest that there really is a relationship. We have evidence to suggest that there is a true relationship between the dependent and the independent variables. Okay? That's different from practical significance. Practical significance is that the magnitude of your coefficient is large enough to actually influence economic theory or policy. Is the effect actually big enough to matter? That's practically significant or economically significant. And just because something's statistically significant does not mean that it's practically or economically significant. So let me give an example. Let's imagine that we want to know if a government should subsidize a microfinance program. All right, microfinance program, that's small loans for small businesses. And a government might subsidize a microfinance program, give banks money so that banks can offer loans at a lower interest rate. They might do that because they think that if small businesses have access to loans, that those businesses are going to be able to grow, and that will improve incomes and livelihoods for small business owners. Okay, and we want to know, well, should the government subsidize this microfinance program? The cost per microfinance client would be $10 on average for the subsidy. All right, so with the subsidy, okay, we run a regression. We find that the impact of microfinance loans, we run a regression to find what the impact is of microfinance loans on small business profits. Or really, I should say the relationship. What's the relationship between having a microfinance loan and a small business's profits? And we find a statistically significant effect at 1% level. Very significant, very statistically significant, that microfinance loans increase profits. All right. So we find very statistically significant result that having a microfinance loan is related to increased profits for small businesses. Now, just from that result, we might say, all right, done, good, excellent. Policy recommendation, subsidize those microfinance loans. However, the coefficient, although it's very significant, the coefficient is only $2. The coefficient is 2. Is this practically significant? Well, in a certain sense, we could say yes. We could say yes in the sense that it would suggest that they should not implement this microfinance program subsidy. But in another sense, it's not practically significant because we have provided no evidence to suggest that they should subsidize this microfinance program. If the impact was larger than $10, we'd say, okay, yes, we have provided evidence that you should subsidize the microfinance program. Okay, a similar example would be, let's say we're not talking about a subsidy, or let's say we don't know what the price of the subsidy would be. And we find that the impact is statistically significant, but it's only, instead of $2, it's only like 2 cents. It's like, yeah, okay, that's statistically significant, but 2 cents is such a small effect that it just doesn't matter. It's not going to affect policy. We're not going to come up with some scheme to help increase microfinance programs because having access to a microfinance program just doesn't help very much. It's statistically significant, but it doesn't drive policy. Okay. All right, and then one last point is that if a variable is very insignificant, so a large p-value, we might consider dropping it from the model. But we always have to be careful. Because remember, the primary justification for a model is theory, not data. We always start there first. There could be reasons why a variable is insignificant but still should be included in a model. But if a variable is questionable from a theoretical standpoint and highly insignificant, then we might consider dropping it from the model. All right, last topic before the demo, goodness of fit. Now we talked about this in the simple regression model. We talked about goodness of fit. How well does the model match the data? And we used the R-squared. But now that we've got multiple variables, we're going to look at two more goodness of fit measures. All right, so remember R-squared. There's one major problem with R-squared. The problem with R-squared is that it increases every time that you add a new variable. It increases, or it might stay the same. It might stay the same or increase, even if the new variable is irrelevant. So for a multivariate regression model, R-squared might not be the best measure of goodness of fit, because if every time you add irrelevant variables, R-squared goes up a little bit, you might conclude that you're getting a better model when you know that you're not, because you're including irrelevant variables. So we might need an additional measure of goodness of fit that is able to accommodate this problem. We call this the adjusted R-squared. We use the adjusted R-squared. The adjusted R-squared is just like the R-squared. It's a number between 0 and 1, where the closer you are to 1, the better your model fits the data. But R-squared is constructed in such a way that it will penalize you for including irrelevant variables. So adjusted R-squared only goes up if you add relevant variables to the model. We'll talk in a future lecture about how we calculate adjusted R-squared, and you can see how that works. The last goodness of fit measure that we'll talk about here is the F-test for goodness of fit. So I just mentioned in an F-test, in a multiple restriction test, we can say we can set a bunch of parameters equal to 0 and see whether or not these parameters jointly equal 0. Well, if we think about it, if I do that test on every variable in the model, every coefficient in the model, if I say, well, beta 1 equals beta 2 equals beta 3 equals beta 4 equals 0, I can use an f-test for that. And if the coefficients in my model are jointly significant, that means if we reject the null hypothesis that all the coefficients in the model are equal to 0, that would be an indication that we have a model that does explain some of the data, that does explain the dependent variable to some extent. So we can use an f-test also as a measurement of goodness of fit, which we will see in today's demo. All right, with all of that said, let's demo all of it. Let's get an idea. Let's go through all these issues in our demo in Stata. So I'm going to go here. I'm going to open up Stata. All right, in typical fashion, I'm going to pull that to one side. I'm going to open up a do file, put that to the other side. I really like this and recommend it. All right, and I'm going to open up our data set. Let's see, data sets, and I'm going to use wages too. All right, so we're going to use our wages example here. You can see our variables. We've got wage, education, experience, non-white, female, married, and job. All right, now let's do it. All right, lecture number 4. All right, multivariate regression model. All right, let's go through this step by step. First, what's our question? We want to develop a model. What's our task? Develop a good model to explain wages. All right, there is our task. Now, as we talked about in lecture, the very first thing we do is we think about theory. What makes sense? What is the model that makes the most sense? Now, as we thought about it in class, we said, you know what, I'm almost sure that we might even make a list here. We might even make some notes. I'm almost sure that education is going to be important. So let's see here. Important variables. Education, experience. Those are my top ones. Those are definitely those are the top of the list. All right, those are the top of the list. Education, experience. All right. Maybe non-white. I would hope not. Maybe female. Maybe married. We might not think, okay, marriage probably doesn't cause anyone to have higher incomes, but you might expect that people that are married are probably farther along in their career, and so marriage might be correlated with higher wages. But it's hard to see how it would be causal. Unless we say, okay, married people, because married people tend to be happier, married people tend to be more efficient, and more efficiency increases your wages. Okay, we might be able to come up with a story there. All right, and actually probably job. Probably job. But you know what? I'm going to come back to that one later. So let's do our first model. First model, we're going to say wage is a function. Wage equals some function of education and experience. All right, that's going to be our first model. So let's think about that. Now we might jump straight to a regression. Reg, wage, education, experience. But let's let our data talk a little bit. Let's let our data talk. Do we think that this is even true? I like to do scatter plots a lot because scatter plots just help me understand what's going on in my data. So let's run a couple scatter plots just to get an idea of whether or not our intuition here makes sense. Education, experience, all right? And we might even try to get a little bit more. Actually, let's start here. Let's just start with these two. Do we think that from running these scatter plots, do we get an idea that that there's a relationship here? Well, do you think it's increasing, flat, decreasing? I look at that and I think, you know what? I think that there's an upward trend. All right, that kind of confirms what I was thinking. More education means more wages. All right, that makes sense. What about experience? Ooh, that's not terribly obvious to me. Do you think that's increasing? Or what do you think? Is it flat? Is there no effect? Actually, might you say that there's a nonlinear relationship? Like it kind of starts low, and it gets bigger in the middle, and then it comes down lower at the end? With looking at this, we might think, you know what? It's not very strong, but we might think this is nonlinear. We might think that we might consider later including a squared term for experience. Now that we look at this, we might include a squared term. Let's think about that later. Let's come back to that. All right. I think we've got a good reason to include these variables, so let's run it. This is our first model. What do we find? All right. Education increases wages by 65 cents per hour, significant at the 1% level. Experience also increases wages by 7 cents per hour, significant at the 1% level. All right. Okay, that's pretty good. Hey, let's check out some of our goodness of fit measures. You'll notice here we've got R squared, which is 0.2259. We also have adjusted R squared. All right, this is our new one. This is the one that penalizes you for the addition of variables. It will only go up if you add relevant variables. Okay, so it's starting out at 0.2230. All right. I also mentioned this the F test, that we use the p-value of an F test. Well, this right here, this what you see right here is the p-value from an F test that tests the hypothesis that beta 1, the coefficient on education, and beta 2, the coefficient on experience, are both equal to 0. All right? It tests the null hypothesis that both are equal to 0. We find that the p-value is very small. That means we reject the null hypothesis. We have evidence to suggest, strong evidence to suggest, that education and experience are not both equal to 0. That means these variables do probably explain wage, the outcome variable. All right, so here we go. We've introduced ourselves to our new measures of goodness of fit here. All right, but now let's keep thinking. What else might be relevant? Now I said before, okay, well maybe ethnicity and the individual's sex, so maybe if they're non-white, or maybe if they're female, that might affect it. Okay, well let's explore that intuition. Wage, non-white. We're going to use a scatter plot here. These scatter plots are going to look a little different because these are dummy variables. All right, but we can still get an idea. Let's run this one. What do you think? There's a lot less data. There's a lot less data for people that are not Caucasian. But you might think, just by comparing, it's a little hard to tell. You might think that maybe they've got a little bit lower income. All right, what about female? You know what? The same thing. It's a little bit hard to tell. Maybe female's a little bit lower. All right, so we're a little bit unsure. Unsure, but let's go ahead and do it. Let's go ahead and run the regression. Let's include it, and let's see what happens. Is non-white and female, are they irrelevant? Are they irrelevant? If they're irrelevant, we should leave them out. If they're relevant, we should include them. All right, so let's think about this. Let's look here. We've got education, still significant, pretty similar to what it was before. Significant 1% level. Experience, pretty similar to what it was before. All right, significant at the 1% level. All right, we've included non-white, not significant, very large p-value. All right, ethnicity might not be very relevant. All right, female, negative, okay, highly significant, significant at the 1% level. Okay, now let's look at our measurements of goodness of fit. Has our R squared go up? Well, we would expect it to because we've added variables. So that might not be as helpful. What about our adjusted R squared? Adjusted R squared will only go up if we've included or if we've introduced relevant variables. So let's compare one. We've got 0.3044, and before we had 0.2230. That means this new model fits better. We've included relevant variables. Okay, but now we might think, well, non-white is highly insignificant. All right, well, let's give this a shot then. We might think non-white might be an irrelevant variable. So let's drop it. Let's drop a variable that we think is irrelevant, and let's see what happens with our adjusted R squared. All right, so let's run that model. All right, so now we've dropped non-white. We're a little bit concerned that that was an irrelevant variable. All right, it was very insignificant in the first regression. All right, so now we're running the model without non-white. Okay, all of our coefficients are pretty similar here. Let's compare our adjusted R squared. Our adjusted R squared without non-white. Actually, let's do R squared first. Let's illustrate this. R squared without the non-white variable is 0.3096. Now, as I said before, every time you add a variable, whether it's relevant or irrelevant, R squared will go up. So let's check that. R squared, this is the model that had non-white in it. R squared, 0.3097. So R squared is higher when you include non-white, even though we think non-white's irrelevant. All right. Well, let's look at adjusted R squared. Like I said, when we include irrelevant variables, adjusted R squared can actually go down. It punishes you for irrelevant variables. All right, so let's check it. Adjusted R squared without non-white is 0.3057. So if non-white really was irrelevant, we would expect that the inclusion of non-white would give us a lower adjusted R squared. So let's take a look. Our adjusted R squared, when non-white is included, 0.3044. There we have it. Adjusted R squared actually goes down when you include non-white. That's good evidence that this is an irrelevant variable and we don't need it in the model. Okay, now let's think a little bit more. As we went through the regression, as we went through the lecture, we talked about we might want to include variables. We might want to include variables that are interaction terms, variables that are some combination of the variables that we already have in our data. We might want to include an interaction term. We also might want to include a squared term. Do we have any reason? So let's think about this. Additional terms. Interaction or squared. All right. So let's think. Do we have any justification for an interaction term or a squared term? Well, we already mentioned earlier when we took a look at that scatter plot between wages and experience. I might bring it back up here. We already talked about this earlier. We said, oh man, it's kind of hard to tell what's going on here. But you might be able to argue that there's a little bit of a nonlinearity here. You might be able to argue there's a little nonlinearity. In that case, we might want to include a squared term. So let's do it. Let's just do it and see what happens. Experience 2. X per 2. That is going to be, gen X per 2 equals X per times X per. All right? So we're going to generate a squared term. Let's go ahead and generate an interaction term at the same time. What do we think might be relevant? An interaction term that might be relevant. How about, let's see, what do we think? We might think that the sex of the individual, so female or male, might be related to, let's say, education. Maybe women have a higher return to education than men, or maybe the vice versa. So let's do it. Let's do fem EDUC. We're going to interact those two. All right. Education times female. All right, so now we've got an interaction term. We've got a squared term. Let's check it out. Let's run our best model so far. Wage, all right, as a function of education, a function of experience, a function of female, and now a function of experience squared, and a function of the interaction term between female and education. All right, we're excluding non-white because we think it's irrelevant. Let's run it. Boom. All right, what do we got? We've got education, okay, experience, female. Now female's insignificant. That's interesting, okay. We've got experience squared. Experience squared is highly significant. Significant at the 1% level. We might be right. There might be a nonlinear relationship between wage and experience. All right, and then what do we have here on our interaction term? Our interaction term between female and education is negative, okay, but it's insignificant. Okay, so now that we've included this interaction term, we don't find anything related to the sex of the individual. All right, but we have some interesting stories to tell here with experience. So we find that, okay, as experience goes up, your wages go up by 25 cents per hour. But that is only for so long. As experience continues to go up, every additional year of experience has a smaller impact on wages. So every additional year of experience has a smaller effect on wages. So if I have no years of experience to start with, the first year of experience that I have will be worth 25 cents an hour. Well, I should say 25.4 cents per hour. But if I have 1 year of experience, an additional year of experience, if I already have 1 year of experience in my bag, then an additional year of experience would be only worth 25 cents because I'm subtracting this 0.004. Let me illustrate this. Let me go into the lecture. I'm just going to illustrate this, okay? I'm going to illustrate this live. All right, where's my interaction term? Squared term. Here we go. I'm going to make a new slide. Live action right here. All right. We're doing a squared term right now. Squared term. All right, get rid of that. Experience squared. Actually, we have a slide on this. All right, let's bring the slide in. We got a slide. Here we go. All right. Here we go. There we go. Let's just do this. Boom. Much better. All right, so we already got it. We're interpreting experience squared. We've got experience squared in the model. All right, now the best way to do this is we take the derivative of wage with respect to experience in order to interpret this. So let's do this. What is beta 2? Beta 2 is 0.254, all right? So now we're 0.254. What's beta 3? These are estimated beta 3s, right? All right, it's negative 0.004. Okay, we're just rounding off. All right, so now this is what we have. This is going to be our experience. This is going to be our impact of experience on wage. When you have 0 years of experience, what does this equal? Let's bring up my calculator. When you start out with 0 years of experience, what do you have? You have 0.254. You just have beta 2. The impact of experience on wages when you have no experience to start with, it's 0.254. But if you start out with 1 year of experience, so if experience equals 1, then it's 0.254 minus 0.004. So now the impact of experience on wage when you start out with 1 year of experience is now 25 cents an hour. Well, let's say that you start out with 10 years of experience. So let's do it. 0.254. Now let's assume you start out with 10 years of experience. That means experience equals 10. So then I would subtract 0.004 times 10, and that would equal, okay, I'm not doing this right, 0.2, 0.4. Okay, I'm just going to do the other calculation in my head. This would be minus 0.04. All right, so now the impact of experience on wage is 21 cents per hour. So you see, as experience goes up, the marginal effect of an additional year of experience is smaller. And that's what beta 3 is telling us. That's what this beta 3 is telling us. Well, okay, in here it's beta 3. In here it would be beta 4. But either way, the coefficient on the interaction term is telling us how the change in experience affects wages given a change in experience. That basically there's a nonlinear relationship. Every additional year of experience is worth less because this is negative. If this were positive, every additional year of experience would be more. It would apply larger increases in wages given a change in experience. Okay, so I hope that helps with that interpretation. All right, so now if we were to interpret our interaction term, how would we interpret our interaction term? Well, they're insignificant. If they're insignificant, we actually just assume that they're zero because we don't have any evidence. We don't have any evidence to suggest that they're not just zero. Our null hypothesis for coefficients is that they equal zero. And the only way we reject that is if it's statistically significant. And these aren't. And so I actually would just say these are both zero. And there's really no interpreting them. So the interaction between education and female just doesn't do much for us. Let's do another one to give us the ability to interpret it. All right. Let's do the one that we talked about in the lecture, an interaction term between education and experience. All right, so now we're going to interact education and experience. Let's generate that. All right, and now to avoid complications of interpretation, I'm going to get rid of our squared term. I'm going to write a new line. Rather than just deleting it, I'm going to write a new regression line. All right, I'm going to get rid of the squared term. Get rid of the interaction term that was irrelevant. Education, experience. All right. Let's run this. Okay. Again, they're just insignificant. The interpretation would need to just be zero. All right. So let's try another one. Let's see if we can find a significant interaction term. What about education and married? EDUC, MAR. Whenever you include an interaction term, you need to include both of the terms that are involved in the interaction separately. Okay. Again, we're striking out. We're not finding a statistically significant interaction term in this data set. All right, I'm going to try one more, and if we don't do it, I'm just going to do a mock interpretation. Education, non-white. Education times non-white. Non-white. Okay. Education, non-white. Generate it. Okay. So let's just treat these as if they're significant so that we can, let's just treat this as if it's significant so that we can interpret it. All right, so we can get some practice interpreting. All right, so let's go up. I'm going to grab a slide that does the interpretation of an interaction term. All right, and let's just delete all this. Let's make this bigger, and right. And we are going to interpret this term. All right, so now we're doing non-white. All right. Now, if we wanted to think about some intuition here, why would we do this? So non-white seemed to be irrelevant before, but maybe there's an interaction between them. Maybe education has a big return for a bigger return for non-white individuals in the economy. Maybe there's a larger return for individuals that are not white. So we might think this. We might use our intuition to say, all right, I think that there might be an interaction here. There might be a larger return to education. All right, so let's say we've done this, and now we're going to interpret it. So let's take our values here. We've got education. So beta 2 is going to be 0.061. And then beta 3 here from our model, beta 4 from our model. The coefficient on the interaction term is going to be, let's plug this in, all right, negative 0.075. How do we interpret this? What we would say is that if you are white, that means non-white equals 0. All right, if non-white equals 0, then the impact of education is 0.61. All right? That's how we interpret that. If the person is non-white, all right, that means non-white variable equals 1, then it would be, then the impact of, where's my calculator? Then the impact of education on wages is 0.61 minus 0.075. All right. So the impact of education on wages is 0.61 if the non-white variable equals 0, and it is 0.535 if the non-white variable equals 1. Okay, but actually we know that it's insignificant. That means this effect isn't here. That means this beta equals 0, this all goes to 0, and there is no effect. Okay. All right. Now let's go back here. Now let's think. We might want to do, let's go back to the best model that we have. So far we think that education, experience, and experience squared are all important factors in determining wage. Well, we also said female. So we've said education, experience, sex, and experience squared are all important factors that determine wages. All right. Now let's say we want to do a joint test. Let's say we want to know, well, what's more important? Is education or experience more important? So we're going to do a joint test. We want to know what's more important. Joint test. Let's do it. What is more important? Education or experience? All right. Or we could say, is one of them more important? All right, we might want to know that. That might be really interesting to us, is to know whether or not there's a difference. So if we want to do that, we would perform a joint test. And in this case, all we do, it's very straightforward, test. We're going to test the hypothesis. Actually, let's state our null. Before we do it, let's state our null. Our null hypothesis is that the coefficient on education equals the coefficient on experience. That's our null hypothesis. Our alternative hypothesis is that the coefficient on education is not equal. This is the status symbol for not equal. Does not equal the coefficient on experience. All right. So let's test that. If we reject the null hypothesis, then that means that education and experience are not equal to each other. And we can just look at the coefficients. We can say which one's bigger. If we fail to reject the null hypothesis, then we actually cannot say that one of them is larger than the other. All right, so let's test it. Education equals experience. That's how we do it. We just run the regression and we do test education equals experience. All right, we get our results. Down here we see the results of our test. And we find that the p-value is 0.0000. Very small p-value. We reject the null hypothesis at a 1%. That means that we can look at these coefficients and we can say whichever one's bigger actually is larger. So we can say, okay, education, it's larger than experience. That means education is more important, the more important determinant of wages than experience. Okay. The last thing I want to do is I want to come up, let's think, all right, what is the best model that we can think of? Now, there's a variable in our data set that we haven't taken into consideration yet, and that it's job. What sector does the individual work in? But based on intuition, we would think that might be really important. What sector might be really important? So let's make a model that includes that. If you remember from the lecture, what we need to do, because job is a categorical variable, we can see that. Let's open up the data and take a look. Job is a categorical variable. So we can't just run job in a regression. You want to see what that looks like? Let's see what it looks like. Reg, wage, job. What happens if we try to run a regression with a categorical variable? No observations. It doesn't work. Okay, you can't run it with a nominal categorical variable when the entries are strings. That means when they're words. Doesn't make sense. Okay. So to do this, we need to create some dummy variables. We need to create some binary variables that indicate each of the possible jobs. So let's do that. I'm going to come over here and put tab job. All right, and that's going to give me the names of the different jobs in the data set. All right, and I'm going to create a dummy variable for each of them. I'm going to do manu equals job equals be sure you spell this right, manufacturing. All right, and that's going to be a dummy variable that equals 1 if the person works in manufacturing. Then I'm going to do management. All right, equals job equals management. All right. All right, we're going to create a variable for sales. All right, it's going to equal 1 if they work in sales. And then lastly, we're going to create a dummy variable for service. It's going to be equal to 1 if the person works in the service sector. All right, so let's create our variables. Run those. All right, let's check it out. Let's look at our data set. Now we have 4 dummy variables, and we can quickly confirm it. If the person works in manufacturing, manu equals 1, 0 otherwise. If the person works in management, mana equals 1. If the person works in sales, then sales equals 1. If the person works in service, serve equals 1. Okay. So now let's include those variables in the regression. Reg, wage. So let's combine those. Let's add those into the best model that we have. Manu, mana, sale, and serve. All right. Let's add those. Because we think that the job is going to matter. Okay, now, before I run this, remember back to the lecture. I mentioned something called the dummy variable trap. That means you can't include a dummy variable for each of the different categories that correspond to a categorical variable. I've just done this. I've fallen into the dummy variable trap. I've included each of the 4 dummy variables. What happens if I do the dummy variable trap? Let's run it. Chaos. The regression doesn't work. Variables are omitted. All right, let's do it if we don't do the dummy variable trap. We exclude one of them. We have to exclude one of them. Now let's run it. It still didn't work. All right. There's another reason. I've accidentally typed wage twice. All right, there we go. All right, well, let me go back. The real problem in that last one is that I had wage twice. Let me do this again. What happens when we have all the dummy variables? Well, what happens is one of those dummy variables gets dropped. All right, that makes a lot of sense. One of those dummies, they just gets dropped. Stata drops it automatically. All right, so we cannot include all the different dummy variables for a particular categorical variable. So we have to drop one of them. So let's drop the last one. Let's drop serve, and then now let's run it. Here we go. We have our regression results. We actually find that none of our job sector variables are statistically significant. None of them are statistically significant. It would look from this like what sector they work in doesn't actually matter. It looks like it doesn't actually matter. But now this raises the question, this will be the final thing we do, is maybe they're jointly significant. Let's do our F-test on a joint null hypothesis. Let's test a hypothesis here. All right. Let's test the hypothesis that really all of those equal 0. Like right now, because we've rejected the null for each of them separately, we've basically said that each one of these equals 0. Well, let's test the null hypothesis. So we're going to do a hypothesis test. We're going to do a hypothesis test. Because we're a little bit suspicious. We would think that the job sector would matter. So we want to jointly test all of them at once. We want to ask the question, okay, if we control for everything else, education, experience, etc., if we control for everything else, does the job sector matter? And the best way to do that, because we've got 3 different dummy variables, the best way to do that is to do a joint hypothesis test that tests the null hypothesis. We're going to test the null hypothesis that the beta on manufacturing is equal to the beta on management is equal to the beta on sale is all equal to 0. We're going to test the null hypothesis that they're all jointly equal to 0. If they're jointly equal to 0, then that really does mean that the job sector, the sector in which they work, does not matter. But it could be that they are jointly significant, which would mean that the job sector does matter, but it's just that we don't see any significance of any particular sector. All right, so let's do a test. Manu equals mana equals sale equals 0. Let's run that test. All right, so here's our test result. Our p-value is large, 0.5996. That means that we would fail to reject the null hypothesis, and so we would say that we do not have any evidence to suggest that the sector that they work in matters, that the sector that they work in is related to the wage. We do not have any evidence that the sector that they work in affects wage. We don't have any evidence that any particular sector affects wage, and we don't have any evidence that the sector in general affects wage. Okay. And that is it for today's lecture. I wish you the best of luck with the assignment. Be sure to follow this lecture and be sure to follow this code and the intuition very closely in order to prepare for next lecture. Come to lecture prepared. As I was talking to some students, one thing that I would recommend doing is while you're going through the lecture, while you're listening to the lecture, actually follow along. Type the code out. Go through the examples with me on your own Stata. All right? Save the do file from the lecture and bring it to class. All right? That'll be very helpful for the next lecture. So with that said, I thank you very much for your time, and I hope that you have a wonderful rest of your day.